In the previous video, we got some basic idea about the vector, unit vector, position and distance vector. Now, in this video, I will be giving you some basic idea about the algebraic manipulation like vector addition, subtraction and multiplication. So let's get started this video. First, we will discuss about how to add and subtract two vectors. So for addition of two vector, we have to take two vector and find the resultant. We can find the sum with two methods. First is parallelogram rule and other one is head to tail rule. Now I will discuss how parallelogram rule is used for finding the sum of two or more vector. Let's take two vectors A and B. Now we have to add these two vectors using parallelogram rule. According to the parallelogram rule of vector addition, if two vectors A and B represent two sides of a parallelogram in magnitude and direction, then their sum A plus B is equal to the diagonal of parallelogram through their common point in magnitude and direction as shown in figure. Similarly, when we talk about the head to tail rule, there is slight change in adding two vectors. To add vector A to vector B, first move vector B keeping its length and orientation in same way as it is until tail touches the head of vector A. The sum is vector from the tail of vector A to the head of vector B as shown in figure. Here, the linear displacement from point A to 3 is known as resultant of geometric sum of the two displacement, that is A, that is 1 2 and 2 3. That means vector A and vector B. Therefore, the sum vector is given by vector C is equal to vector A plus vector B. Now look at some property that is followed by the vector addition. First one is the commutative law, where vector A plus B will be equal to vector B plus vector A. It means you can move vectors around and still you will get same answer. The second one is associative law, where addition of vector A plus B with vector C will be equal to the vector B plus C with vector A, which means you can regroup the sum of vectors, still get same answer. Negative of a vector is a vector which points the opposite direction to the reference direction but it has same magnitude. Now let's take two vector, vector A and vector B. Suppose we want to add vector A to the magnitude of vector B. The resultant will give the subtraction of these two vectors A and B. For solving vector addition and subtraction, procedure is almost same like scalar. Only difference is to maintain the direction associated with vector while doing any algebraic operation. Let's take two vector, vector P and vector Q. Vector P is represented as x cap ax plus y cap ay plus z cap az, whereas vector Q is represented as x cap bx plus y cap by plus z cap bz. So the addition and subtraction of P and Q are represented by R and S respectively. So R is equal to P plus Q, that is the addition of vector P and Q, and it is equal to x cap ax plus bx plus y cap ay plus by plus z cap az plus bz. That and subtraction of vector P and Q is P minus Q. This is basically can be written as P plus minus of Q. That means with the same magnitude and reverse the direction. So we will get x cap ax minus bx plus y cap ay minus by plus z cap az minus bz. For more clear vision, let's take an example of two vector. If two vector P and Q is given as vector P is equal to 7x cap minus 3y cap plus 4z cap, whereas vector Q is equal to 3x cap plus 2y cap plus z cap. Find the component of p along x and the magnitude of 2p minus q. Now first we have to find the component of p along x. Just look at the value of vector p. From here it is clearly seen that x is equal to 7. So component of p along x direction is ax is equal to 7. Now we have to find the magnitude of 2p minus q. As I said earlier, always magnitude component in same direction will be manipulated together. The magnitude of 2p minus q can be written as 2 multiplied by vector p minus vector q component. So after solving this, we are getting 11x cap minus 8y cap plus 7z cap. So the magnitude of 2p minus q is equal to square root of 11 square plus minus 8 square plus 7 square, and this comes to be 15.29. Now I will be giving the basic brief of various ways of multiplication of vectors depending on how they are multiplied. So let's start the next topic, that is the multiplication of vectors. The multiplication of two vectors can be interpreted in three different ways depending on how they are multiplied. First case is product of vector and scalar. Suppose a vector is multiplied by the scalar quantity, then resultant will be another vector quantity having same direction, but the resultant is multiplication of scalar and vector amplitude. For example, vector A is multiplied with the scalar quantity b, so the resultant will be vector c. The vector c will have same direction, but the amplitude is the product of b with the amplitude of vector a. And the second case is the scalar product or dot product. So basically the dot product is Euclidean magnitude, that is the magnitude of two vectors and the cosine of the angle between them. Which means if a vector is multiplied with another vector in such a way that the resultant is scalar quantity, then it is said to be scalar product or dot product. Therefore, the resultant scalar quantity is equal to the product of magnitude of the two given vectors multiplied by the cosine angle between them, and it can be written as a dot b is equal to a b cos theta, where theta is the angle between two given vectors. Let's take some related properties with it. First one is the commutative law. That means a dot b will be equal to b dot a. And the second one is the distributive law. That means a plus b dot product with c will be equal to a dot c plus b dot c. So the question arises, what is the use of dot product? It's very simple. Dot product is often used for the testing the vectors orthogonality. That is to test whether or not taken two vectors under consideration are orthogonal. Just making it simple, if the angle between the vectors is 90 degree, then two vectors are orthogonal. One more important use of dot product is in projection. The scalar projection of B onto A is the length of the segment. Thus mathematically, the scalar projection of B onto A in the direction of A. Here some basic rules are given as unit vector Ax dot product with unit vector Ay will be equal to 0 because angle between unit vector of x and y is 90 degree, so cos 90 will be 0. Similarly, Ay dot product with Az dot product with Ax will also be 0, and Ax dot product with Ax or Ay dot product with Ay or Az dot product with Az will give 1 because the angle between unit vectors along the same axis will be 0. So cos 0 will give the 1 and the resultant will provide the 1. Now let's take two vector A and B in the Cartesian coordinate system, where vector A is given as ax I cap plus ay j cap plus az k cap, and vector B is given as bx I cap plus by j cap plus bz k cap. Taking some special case, that is the theta is equal to 90 and theta is equal to 0 degree. Suppose two vectors are at 90 degree to each other, then the dot product will be 0 as 90 as cos 90 will be 0. So a dot b is equal to ab cos theta and ab cos 90 is equal to 0. Therefore I dot j is equal to j dot I equal to k dot I, or I dot k or j dot k or k dot j will provide the 0 because angle between these unit vector is 90 degree. However, if given two vectors are at 0 degree in between them, then the dot product will be simply product of two vectors, as a dot b is equal to ab cos theta and ab cos 0 degree will provide the ab. If it is unit vector, so multiplied will give the 1. Thus it can be said that product of like unit vector is unity and unlike unit vector is 0. So finally for this we will get the a dot b is equal to ax bx, ay by plus az bz, because rest of the component will be 0, because the angle between the other components will be 90 degree, so cos 90 will be 0. That's why rest of the component will provide the 0 value. Now the third case in multiplication of vector is the cross product. In this case, the cross product is a vector that is the perpendicular to the plane containing two original vectors, that is normal to the plane containing them as shown in figure. Let's take two vectors a and b. The cross product a cross b is defined as a vector that is the perpendicular, or you can say orthogonal, to both vector, that is vector a and b, with a direction given by the right-handed screw rule, and the magnitude is equal to the product of magnitude of two vectors multiplied by the sine of angle between them. The direction of cross product of two vectors is perpendicular to the plane containing two original vectors. A cross b is equal to n cap mod of a mod of b and sine theta. N cap is basically unit vector that is in the direction of perpendicular to the vector containing plane, that is the basically resultant of a cross b. As I told you, direction is defined using right hand screw rule, so it is used when direction must be determined based upon the rotational direction or vice versa. To understand it, grasp the axis in right hand and curl the fingers around in the direction of positive rotation, and the thumb is oriented in the positive direction. Thus, if the direction of rotation is known, then the fingers can be curled in this orientation and the thumb will point in the positive direction and vice versa. In other words, orientation of vectors may vary the direction. You can already see the a cross b and b cross a have the different direction, because the angle framing from A to B will provide the anti-clockwise rotation, so thumb will upward direction, so A cross B will provide the upward direction. In the case of B cross A multiplication, the angle will form from B to A, so rotation of fingers from in the clockwise direction, the thumb will go in the downward direction, so that's why the direction of B cross A will be in the downward direction, and it can also be written as minus of A cross B. That means the direction is just opposite of A cross B. Now let's discuss some properties related to cross product. First is, it does not follow the commutative law. That means A cross B will not be equal to B cross A, as I told you in the earlier slides, because the direction of A cross B will be opposite to the direction of B cross A. A cross B is equal to minus of A cross B. That's why it does not follow the commutative law. Second property is distributive law. That is, A cross B plus C is equal to A cross B plus A cross C. That means vector A is distributed in with B and vector C. And the third property is it does not follow the associative law. That means A cross B with B cross C will not be equal to A cross B with vector C. Let's take two vector A and vector B in the Cartesian coordinate system, which is given as ax I cap plus ay j cap plus az k cap, and vector B is given as bx I cap plus by j cap plus bz k cap. Since the cross product must be perpendicular to the two unit vectors, it must be equal to the other unit vector or the opposite to the unit vectors. Look at the cycle diagram shown here. The standard unit vector in the three dimensions I, j, k are helpful to find the direction of resultant. When you are moving in the clockwise direction, it will give you the positive direction. That means I cross j will provide the k, j cross k will provide I, k cross I will give j. But if you move anti-clockwise direction, you will get negative direction. That means j cross I is equal to minus k cross j is equal to minus I cross k is equal to minus j. Now take some special cases of angle between the vectors which has to be cross multiplied. Suppose we have theta is equal to 90 degree. Then the cross product will result of two vectors as a product of magnitude of two vectors and direction as per cyclic rule discussed earlier, because the sine 90 will be 1. Then we will get I cross j is equal to k, j cross k is equal to I, and k cross I is equal to j. However, the angle between two unit vector along the same axis in a coordinate system is 0 degree. Then we have sine the 0 degree will be 0. Then I cross I, j cross j, and k cross k will be equal to 0. Let's take an example for understanding the approach to deal with the cross product. Take two vector A and vector B in the Cartesian coordinate system. It is given as vector A is equal to ax I cap plus ay j cap plus az k cap. Vector B is equal to bx I cap plus by j cap plus bz k cap. So the cross product can be obtained by solving the determinant. A cross B is equal to I j k ax ay az bx by bz. Therefore, A cross B is equal to ay bz minus az by plus az bx minus ax by plus ax by minus ay bx. This is the basically three component of the ijk, which is obtained by simply solving the determinant of A cross B. Now, a scalar triple product is a dot product of the first vector with the cross product of second and third will produce the resulting vector. Suppose A dot B cross C will be equal to B dot C cross A, and the same will be equal to C dot A cross B. And the vector triple product is defined as the cross product of the one vector with the cross product of other two. That means A cross B cross C is written as B A dot C minus C A dot B. Basically, this is called as Bakayab rule. For example, I have taken here two vector P and vector Q. We will solve this two vector to find the dot product and cross product. So vector P is given as minus 3i plus 2j minus k, and vector Q is given as 2i minus 3j plus 2k. So for the dot product is equal to ax bx plus ay by plus az bz. Because I told you in the earlier slides, the rest of the component will provide the 0 value because the angle between the other two will be 90. So cos 90 will 0. So only remaining term will be here. That will be the component of only same axis term. So after solving this value, we will get minus 14. And the cross product for this given vector P and Q, we can write P cross Q is equal to ijk ax ay az bx by bz. After putting value in this determinant, we will find I plus 4j minus 5k. As the multiplication of two vector, that means cross product, will provide the vector quantity. So here we have the vector quantity. So the dot product of p and q is a scalar quantity in the dot product, that is minus 40. Thank you for watching this video.